To understand the primitive unit cell of the BCC structure, I have a model here, and as you can see, it is somewhat difficult to visualize the primitive unit cell of a BCC crystal. To understand this, you will have to visualize that there are actually 1, 2, 3, 4 unit cells in this conventional representation, which are put together to actually generate the parallelepiped, which is outlined in green here, the faces, green faces, which is the primitive unit cell of the BCC crystal. This vertices, there are 8 vertices to this parallelepiped, and as you can see, 4 of these vertices are the body centering atoms. There is one here from this top unit cell, one from the bottom unit cell, one from the left unit cell, and one from the unit cell in the front. So, you have 4 of those which belong to the BCC positions, and there are 4 which are the original corner positions, like the one here, and for instance the one here and the one at the back. So, you can see this is a rather oblate kind of an parallelepiped, but nevertheless we have already seen that all kinds of parallelepipeds are space filling. So, this primitive unit cell will also be a space filling unit cell which will fill entire space, and often, as you would have noticed, that we do not use this as a conventional unit cell, we use the one which is represented by these red outlines here. The volume of this parallelepiped is half the volume of the other conventional unit cell, as you can see, because there is only one atom associated with each unit cell here, and there are 2 associated with the normal conventional unit cell. To tell you once again that actually it is very difficult to visualize this unit cell even with a model in hand. So, therefore, if you do not have a model in hand, you should pay particular attention to understand that how actually this unit cell is constructed. So, let me rotate this model a little bit for a few angles, so that you can actually see how the unit cell looks from various angles. So, as you can see, this is actually a double L kind of shape. So, there is one L like this, and there is another L like this, and this has an extent in 4 unit cells. So, let us return to the main slides after having looked at this primitive unit cell of a BCC, and let us take up the diamond cubic structure. We have already dealt with this structure in at least somewhat detail, but we will take up some more aspects of the structure which we have not seen before, and also revise some of the familiar concepts. We said that, for instance, no metals crystallize in the diamond cubic structure, but still this is important for us from the point of view of understanding structures. The common elements which crystallize in this structure are carbon, silicon and germanium, and as we shall see later in the chapter on when we talk about covalently bonded structures, that carbon also has other allotropic forms, but one of them is diamond, which, as you know, is the hardest material in nature. And we also noted this important point, that the structure is not a closed pack structure, it has no closed pack planes and has no closed pack directions. So, what I am emphasizing here is the fact that just because I call something an SNF crystal belonging to the FCC lattice, it need not be a closed pack crystal. So, this is one example of that. This also, as I told you, is an important example to illustrate another point, that actually the structure does not have a true 4-fold axis, and still it comes under the cubic class, which essentially implies that 4-fold is not a true 4-fold, that means a pure rotational 4-fold is not a requirement of cubic crystals. So, that another aspect which we have seen. We already seen a model of this diamond cubic structure. I will take that model again to show some important aspects, like how the atoms touch actually. So, what I have is here is the model which I had shown before, and the important point which we will emphasize again using the slides is the fact that every atom, all the atoms here are carbon of course, or germanium if the structure is talking about germanium, or silicon, every atom is tetrahedrally bonded. That means, suppose I pick up an atom, then there are 4 atoms which are at the vertices of a regular tetrahedron. So, for any. So, this kind of a tetrahedral order propagates in 3 dimensions. Suppose I start from the origin here, then I would have an atom here which is tetrahedrally bonded, then this atom would be tetrahedrally bonded, this atom is tetrahedrally bonded. So, if you see that how the atoms touch each other, they actually touch along the 1-on-1 directions, but the touching does not propagate. So, it actually bends off into these tetrahedral angles, and therefore, there is no single direction which is a closed pack direction. Now, this is the conventional unit cell of the diamond cubic structure, and as you know, because this is based on the FCC lattice, it has got 4 lattice points per cell, and each lattice point is occupied by 2 carbon atoms. If it's a carbon diamond I am speaking about, one at 0, 0, 0, other is at quarter, quarter, quarter. Therefore, there are 8 atoms in a single unit cell. 4 of these atoms would be on the outer side of the unit cell, and 4 of them are contained within the unit cell, which themselves form a tetrahedron. So, let us see that tetrahedron, which is the 4 carbons which sit inside the unit cell, which are marked here as the outline of this tetrahedron. You can see here. So, this itself is a tetrahedron, and as you know, a tetrahedron, when you look from upstairs, has got only a 2-fold symmetry, or if you want to look in terms of a roto-inversion symmetry, it has got a 4-bar kind of a symmetry. Now, let us look at other views of this diamond cubic structure, and for instance, this view bottom here shows along the 1, 1, 1 direction. So, you can, and I have clearly marked the atoms in tetrahedral positions inside with this light blue color, the one sitting in the face centering position as dark blue color, and the remaining ones are maroon or brown color. So, please note all atoms are of the same kind, they have been colored differently for better visualization. So, I have an atom here which is seen here at the top in the 1, 1, 1 projection. This atom is hidden below this atom. These 3 atoms are seen as these 3 atoms, and the 3 blue atoms are above those. And finally, you have the hexagon formed by these other outer carbon atoms. And as I pointed out, any atom is touching 4 other atoms and is tetrahedrally bonded to the 4 by the sp3 hybridized bond. So, this is how the diamond cubic structure is, and we have to remember this is not a close packed structure, even though it is based on the FCC lattice. So, you have the lattice which is FCC, and 2 atoms form the motif, the O and T atoms which are 0, 0, 0 and quarter, 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 and therefore, here the motif actually consists of 2 identical atoms. I could alternately choose my origin instead of O at T, and I would find the structure remains unaltered. So, that is another important point to be noticed. So, either the O and equivalent atoms form a lattice, or the T and equivalent atoms form a lattice, and correspondingly O and T would be the motif. As I mentioned, every atom, irrespective of where it sits with respect to the unit cell, for instance, it could be atom sitting on the face, it could be an atom sitting on the corner, or it could be atom sitting in the quarter, quarter, quarter position. All of them have tetrahedral coordination around them of identical type atoms. Of course, the atoms which are in around the central atom have been shown in small size for better visualization. So, you can see that this is my central atom which is in the face centering position, and you can see that there is a tetrahedra of carbon atoms around the central atom. So, for this one. So, this is my coordination polyhedron which is a tetrahedron, and this also reflects the bonding characteristic which I told you is the normal tetrahedral bonding. And again, to emphasize the point, irrespective of where the carbon atom sits, its environment is identical and tetrahedral. Okay. So, there is no difference between the atom which is sitting at O and the atom which is sitting at T, and this aspect has to be clear because with respect to the unit cell they may look very different, but they are identical. Now, these are some advanced considerations, and few things out of this we need to focus upon. The remaining can be left for study, for later study. Is the important thing I mentioned, that this structure does not have a true 4-fold axis, and still it comes under the cubic class. And the reason it is still comes under the cubic class is because it has got a 3-bar axis still. If somebody were to write down the formal space group of the structure, he will call it an F, 4 1 by D, 3 bar 2 by M, where the D actually is a special symbol which stands for the diamond glide. So, it is a glide of the type which is shown here by the red arrow mark, which translates by quarter, quarter. Now, if I look at this structure, the important descriptive symmetry is the 4-1 screw axis and the 4-3 screw axis. So, every one of these perhaps is a 4-1, and every alternate set which is diagonally located is a 4-3 screw axis, and the 4-1 screw axis is connected to the 4-3 screw axis by a diamond glide. As we know, symmetry operators just do not act on atomic entities, but they also act on other symmetry operators present in the structure, and therefore, you can see that they are connected by a diamond glide. So, we have to remember that this diamond cubic structure actually does not have a true 4-fold axis, but it still has a 4-1 kind of a screw axis, and therefore, in international tables, for instance, you would find a point group written as 4 by M, 3 bar 2 by M. Okay, so, this basically reflects the fact that it has got a 4-1 screw axis, even though it does not have a true 4-fold axis. So, these are actually 4 unit cells which I have shown here, wherein I have superimposed some of the screw axes in the structure, and you can see the screw axis does not pass through any of the atomic positions, it passes between the atomic positions, and the diamond glide actually connects an atom at z equal to 0 to the atom at z equal to 4. So actually the glide reflection plane is at Z is equal to 1/8. So it is located at 1/8 the height, and therefore it will move an atom at Z equal to 0 to Z equal to 1/4. Okay. And that's this vector shows only the direction of the diamond glide and not the glide plane itself. Now we switch somewhat gears and try to define a quantity known as density, and the reason we have to describe what is density here is because in usual normal terms density is mass per unit volume, but in material science we have other kind of densities, and we have to remember that often when you are talking about density we are talking about some of these other numbers, and therefore we should not be confused by the units they have. For instance, linear density could be mass per unit length, which is kg per meter, or we could actually be counting number of atoms in a unit length of which typically you would take a straight line, of course. So atoms per unit length, so that will be a number per unit length, so units will be per meter. You could have a length occupied per unit length of material. So suppose there is some linear, and suppose you talk about a one dimensional crystal or a one dimensional line on which you have an atom. So certain part of the line will be occupied by atoms, so I will count that fraction which is occupied by atoms, and I can calculate a linear density. So just show you a figure in the board. So what I mean here, suppose I draw a line through the crystal and I have an array of atoms here. So I will find out, suppose of course this is my unit cell length, I know that this is going to be a repeating infinite unit. So part of the line which is occupied is this part of the line, and the total, suppose this is A and say this is R. So my total will be 2R by A, and this, since it is length by length, it is a dimensionless quantity, but still remember this is a kind of density I am defining. That means that it is a length fraction which is being occupied by atoms along this length, this line. So apart from linear density, you could have areal density. So we saw that even in linear density, for instance, we have various units, like for instance you have kg per meter, you could have number per unit length, which means basically per meter, you could have meter per meter, which is basically dimensionless. And as I will emphasize once more later, but note the useful way to write these quantities is not to factor out the common terms. That means when I am writing meter per meter cube, write it as meter per meter cube and not as per meter square, because meter per meter cube is better instructive of the kind of quantities I am dealing with and is physically a better representation of the density I am talking about. So when I am talking about areal density, again I can go for mass per unit area, which would mean kg per meter square, and when including areal density, I perhaps would include those atoms whose center of mass lies on a particular plane. Like for instance, when I am doing this calculation here, I can do the linear density calculation in two ways. Suppose I have a line here and assume that there are some atoms which are center of mass coinciding on the line. There could be other atoms which do not have center of mass coinciding on the line. In such cases, I have two options at my disposal. Either I include only these atoms whose center of mass coincides with my center, or I include all atoms whose center even does not coincide. That means I will include these lengths. So let me mark those lengths. So possibility number 1 is to include these lengths. Possibility number 2 is to include those lengths and additionally these lengths. So whenever I am doing the definition, it has to be absolutely clear which of these two definitions I am using to actually calculate my linear density. And similarly, when I am talking about areal density, I need to know if I am actually including only those atoms whose center of mass coincides with the plane, or I am including those atoms also whose center of mass does not coincide with the plane. That means that there is only a part of the atom which lies on the plane. So again, I have areal density defined as mass per unit area, which would be kg per meter square, or it can be atoms per unit area, which it means is basically a number density, number areal density, which means it will have units of per meter square, or it could be an area occupied per unit area, which would mean it is meter square per meter square. Okay. And when I am talking of number per unit area, typically I would exclude those atoms. In typical calculations, I would exclude those atoms whose center of mass does not lie on the plane. But then you can extend the definition and include those also, depending on the kind of need you have. Finally, the volume density. Again, you can define mass per unit volume the way you had defined mass per unit length and mass per unit area. So only thing is that here it will be kg per meter cube. you are going to count the number of atoms in a unit volume, which will be a number per unit volume and which will have a units of per meter cube. Or you can calculate volume occupied per unit volume, and we have seen that this is the definition we will use, and we have somewhat been mentioning this before, is the concept of the packing fraction. So, here I would write my units as meter cube per meter cube, just to emphasize the fact that it is volume per unit volume. I can of course cancel out the units and say that it is dimensionless, but I would prefer not to do that, just to emphasize this aspect. The volume occupied per unit volume, as I said, is also called the packing fraction, and we have been dealing with this number before, though we have never formally defined it. Since we are talking about these density, in this context certain other important quantities are like length per unit area. For instance, you could define a length meter per meter cube, and later on we will see this is a very important definition in the context of dislocations. And for instance, we would like to define the length of a dislocation lines, for instance, per unit area of interface. So, this is in the context of interfacial dislocations, or even in the context of dislocations I may want to define length per unit volume. That means I would like to find out what is my length of dislocation line in a volume of material. So, again I will write it as meter per meter cube, just to emphasize that it is length of a dislocation line in a volume of material. Of course, suppose I am talking about a length of a certain line, I do not have to have a continuous line. In other words, I could have curved lines, I could have broken lines, etc. Just to draw a schematic, suppose this is the volume of material I am considering, a cubic volume. Of course, you could also consider a spherical volume, and now I am talking about some entity which is a linear entity, and in this context we are using dislocations. Of course, we are not formally defined dislocations in this course, we will do that later, but for now you need to consider them as lines. So, you have a line here, and suppose I have a line going through and finishing here. So, it is not only not a straight line, it is a curved line, and this is somewhere embedded somewhere in the volume of the material. There could be other lines which go like this, and there could be other lines which go like this and finish here. Of course, these are continuous lines, but there are in pieces. So, I add up all my lines like this, which are in various parts of the crystal, okay, and there could be some lines which will end within the crystal, for instance, there could be loops within the crystal, and I add up all those length of all those lines and divide it by the volume of the material. So, in other words, I have a length of, for instance, in this context, a dislocation line in a volume of material. Finally, I could talk about an areal density, for instance, area per unit volume, and this would be a very important quantity, for instance, in the context of, for instance, grain boundary area or any two dimensional defect. So, we have not defined again what is a grain boundary, we will come to it during a later session, but here we are talking about planes which exist within a volume of material. So, I calculate the total area of my plane. This could be straight planes, this could be curved planes, there could be planes closing on themselves, for instance, it could be a spherical entity, therefore, I have an interface which is a sphere, it could be polyhedral, it could be anything, but I am talking about that surface area of those entities per unit volume of the material. So, these are some of the extended definitions which I need to keep in mind, though of immediate concern only will be this definition, which is the definition of packing fraction, where I am talking of a volume per unit volume. But this is a worthwhile tabulation, that in material science whenever we say density, it is important to remember that what is the kind of density we are talking about. Is it length per unit volume, is it area per unit volume, or is it area per, could be an area per unit area also. For instance, suppose I have a plane and I have a certain set of spherical entities sitting here, I need to know what is the area occupied by those entities on this plane. So, there could be various kinds of density I am talking about, some of them are number densities, some of them are units like kgs, some of them could just be a volume density. I need to know that, and second thing, what are the details in the definition, like I mentioned, am I counting all those atoms who just intersect the, for instance, a particular plane, or am I counting only those whose center of mass lies on the plane. So, these aspects have to be kept in mind when I am defining density in material science. Now, let us explore a little more the packing fraction, and especially the packing fraction of the important crystals we have been considering so far. So, the important crystals we have been talking about are simple cubic, body centered cubic, then the cubic close packed, which is sometimes casually called FCC crystal, the diamond cubic, and the hexagonal close packed crystal. Now, obviously all these have the cubic symmetry, and this has got hexagonal symmetry, and as I define packing fraction, it is the volume occupied by atoms per unit volume of the cell. So, this is what I need to remember. Now, first thing I do is write down the relation between the atomic radius and the lattice parameter. For a simple cubic crystal, since the atom touch along the edges, cell edges, A is equal to 2R. So, there are two. For the body centered cubic, the atoms touch along, we have seen already, touch along the body diagonal, and the length of the body diagonal is root 3a, and there is a central atom which is 2R contribution to this length, and also there are two atoms sitting at the edges of the body diagonal which give a contribution of 2R. So, there is 4R is equal to root 3a. In the cubic closed packed crystal, the atoms touch along the phase diagonal. As you know now, the Miller indices of the phase diagonal is of the type 1 1 0 kind of direction, and therefore, root 2a is equal to 4R. For the diamond cubic crystal, which we have seen before, this is slightly more difficult to visualize. So, let me take up this crystal. So, this is my diamond cubic crystal, and for instance, I am talking about the atom located in one vertex and an atom located at quarter along the body diagonal. So, this distance is root 3a by 4, because my body diagonal is root 3a, a being the edge of the unit cell, and this is root 3a by 4, and this itself is equal to 2r. That means it is twice the radius. That means it is equal to 1 diameter. So, for the body diamond cubic structure, root 3a by 4 is equal to 2r. For the external closed packed crystal, the atoms touch along the, if you are talking about the basal plane, the atom touch along any of the cell edges. So, a is equal to 2r, and c is a little more complicated, it is 4r into root 2 by 3a, which you can derive from simple geometry. Of course, I leave it as an exercise to the reader to actually do this derivation, so that to convince yourself that c is also related to the r. BCC as 2 and the simple cubic as 1 and CP as 2. Number of lattice points per cell, again we have seen is 1 for a simple cubic, 2 for body centered cubic, 4 for cubic closed packed, 4 for DC, and 1 for HCP. The number of nearest neighbors is 6 for simple cubic, 8 for BCC, 12 for CCP and HCP, and 4 for diamond cubic. We will do a sample calculation of the packing fraction for CCP later, but now it is important to note that packing fraction, since it is a volume per unit volume, has the transcendental number pi in its definition. Therefore, whatever numbers we are quoting often as 0.74 is just an approximate number. So, as you know, transcendental numbers go on and on, there is only, we are truncated to 2 decimal places or rounded off to 2 decimal places. The packing fraction of simple cubic is 52%, BCC is 68%, CCP and HCP is 74%, and diamond cubic is 34%. So, again to emphasize the point that the highest possible packing fraction for in nature for sphere packing is only 74%. That means you cannot obtain a packing more than 74% of equal size spheres, and some of the other structures actually have a lower packing fraction. And often you would find that if the element has more covalent character in its bonding, then it will not go for maximum nearest neighbors. Maximum nearest neighbors is promoted by a more metallic kind of bonding where there is no preferential bond angles, and therefore you prefer to have the maximum packing. If you do not have a metallic kind of pure metallic character to the bond, then you might, for instance, the extreme example would be diamond cubic for carbon, wherein the bond is purely covalent. It is not a closed packed crystal. In fact, it has a very poor packing fraction, about 1/3. That means 1/3 of space is actually filled by atoms, and the remaining 2/3 of space is actually vacant. And now for simple cubic structures, it is about 50%, and BCC has about 68% packing fraction. And that is why you might note that very few metals actually crystallize in the simple cubic form. It is only polonium which has got a simple cubic structure, and BCC and CCP and HCP are the more common structures in which you would find metals. So, to summarize this slide once more, packing fraction is described as volume occupied by atoms to the total volume of space, in other words volume of the unit cell. Of course, in doing the calculation you will include only those atoms which are present within a unit cell if you are restricting your calculation to the unit cell. We have the highest packing fraction possible, which is 74% for CCP and HCP, and the others, for instance BCC and simple cubic, have lower packing fractions, and that means more of the structure is actually open. But then we will have to note that just because structure is more open does not mean that you will be able to put more material into those volumes, and some of these aspects we will consider later in the coming chapter. So let us calculate the packing fraction for cubic closed packed crystals. We already know the answer is approximately 74%. So we know that there are 4 atoms or ions in the unit cell. So we want to calculate the volume occupied by the ions by the volume occupied of the total cell. For cubic closed packed crystals, we know root 2a is equal to 4r as the atoms are touching along the 110 direction. So this is my 110 kind of a direction and atoms are touching along. The volume of the cell is nothing but a cube, which is 4r by root 2 the whole cube. So I am just taking it from here and doing the a cube. The volume occupied by atoms ions are each, assuming now I will approximate each atom to be a sphere. So the volume will be 4 by 3 pi r cube, and there are 4 such atoms in the unit cell, will be 4 into 4 pi by 3 r cube. So my packing fraction will be 4 into 4 pi by 3 r cube into 4r by root 2 the whole cube, which is turns out to be pi by 3 root 2, which is 74%. Now the of course there is one small or big step missing in this whole thing, is the proof actually that cubic closed packing or the external closed packing is the highest packing possible, and there is no higher packing possible. So this proof happens to be a very complicated mathematical proof. It was proved within the last 15 years some point of time, and it is actually a complicated proof, and we will not take up the proof here. So sometimes some of these things which have been known for a long time have been proved only of pretty late times, and the proof itself is very complicated and involves a lot of deep mathematics. So for now we will assume that even though there is a proof, we will assume that this is the highest packing fraction possible for equal size spheres. To contradict or to compare my packing fraction of the simple face-centered cubic, which I mean that each lattice point is occupied by a single sphere, with certain other structure which we have considered before, which is the sodium chloride structure, which is also based on the FCC lattice, but now each lattice point is occupied by 2 ions. One is a sodium ion, one is a chlorine ion. So this is my motif here, which we have seen before. So the chlorine ion is at 0, 0, 0, and the sodium ion is at half 0, 0, and we consider this structure as 2 interpenetrating FCC lattices. That means I can place my origin either at the sodium or at the chlorine, and these two, this structure is a super lattice with 2 sublattices, or in other words, this crystal itself is a supercrystal with 2 subcrystals, one subcrystal of chlorine ions, one subcrystal of sodium ions. And the important point I want to show in this calculation is that this is not a closed packed structure, even though it is based on the FCC lattice, and diamond cubic we saw has an even lower packing fraction, but there could be even worse than diamond cubic structures which are also based on the FCC lattice, and we will take up one example later in the course, which is the case of the fullerene. Okay. So we have 4 motifs in the unit cell because it is an FCC lattice. As before, the definition of packing fraction is volume occupied by ions by the volume of the unit cell, and for now we will assume these ions are spherical. Volume of cell is a cube, which is nothing but, you can see the a is nothing but twice radius of sodium ion plus twice radius of chlorine ion, the whole cube, which turns out to be, for the actual sodium chloride structure, is 1.71, 0.88 angstrom cube. Volume occupied by ions is 4 times 4 pi by 3 radius of sodium ion cube plus radius of chlorine ion cube, which is nothing but the simple volume calculation for the spheres, and it turns out to be 114.65 angstrom cube. The packing fraction is the division of these two numbers, which is about 67%, and if you compare it with this table here, it is somewhere around the BCC and not close to the CCP structure. So it has got a lower packing fraction than the CCP structure or the HCP structure. So as I mentioned, you can have structures like the fullerene crystals which are based on the FCC lattice, and fullerene happens to be a beautiful example because it is not a metallic or covalent or an ionic crystal. Actually it is a molecular crystal, and therein you will get even worse packing fractions. Of course there I am talking about packing fraction in terms of the volume occupied by atoms by the volume of the entire space. You could also alternately define the volume occupied by a molecule by volume occupied by space, and that would be alternate definition of packing fraction. I am not taking that definition of packing fraction. We had previously defined the quantity known as atomic density, which was atoms per unit area. So we will see, and this is an important example and important consideration, because we will see that depending on the kind of plane we are considering and depending on the crystal structure, the atomic density changes from plane to plane. Like for instance, and here I am using the definition that atomic density, I am considering only those atoms whose center of mass coincides with the plane in question. Now, the important point note, which this is a conclusion which first I will jump to, then we will see the details. If we take a simple cubic structure, then the 111 plane is the least close packed plane, the 110 is higher density, and finally the 100 has even higher density. On the other hand, suppose I look at an FCC crystal, which is suppose a cubic close packed crystal, the 111 plane has the highest density and the 110 plane has the lowest density, with 100 plane having an intermediate density. In BCC crystals, the order is changed again, and you have the 111 plane with the lowest density like the simple cubic, but here unlike the simple cubic which has the 100 highest density, here the 110 which has the highest density. Now, why is that we need to consider these planes with highest density? Of course, these planes for instance could be performing the role of a slip plane, for instance in dislocation motion, which is very important in plasticity, and so many other considerations we would like to know. For instance, what is my atomic density? Like suppose I am talking about a crystal and what facets would it develop during crystal growth or the equilibrium shape, then the energy it cost for me to put a surface would depend on, of course, on the atomic density, because then I would know number of bonds which are broken based on number of atoms which are there on the surface, and therefore I would like to know my atomic density on each one of these planes. Now, to go through the table, the 100 plane in simple cubic has an atomic density of 1 by a square. So, the area of the square, so let me pick up the square. So, this is my simple cubic structure. I am considering the 100 plane, and if you look at the plane, you will see that this is my unit part of the unit cell, the face of the unit cell, and the volume the number of atoms is 1, which are 4 corners, and the area is a square. So, it is 1 by a square. If you look at the 110 plane, so this is my 110 plane in the simple cubic structure. As you can see, the atoms are only touching along the 100 direction and not along the 110 direction, which is this direction. Therefore, now my area, this is root 2a and this is a, so my area will be root 2a into 1, and the number of atoms is again 1. So, my area will be 1 by a square root 2, and therefore my it is here, it is it is here, it is 0.707 by a square. Now, suppose I look at the 111 plane. Now, the atoms do not touch along these directions. So, you can see along the 111 plane the atoms are well separated, and this length is root 2a, and for I calculate the area of my triangle, which is root 2a into so this is my planar density I am calculating here. Therefore, this area occupied by the atoms in this case would be 1 by root 3a square, which is 0.577. It would be instructive to actually do some of these calculations yourself by considering the triangle and the area occupied by the spheres. Of course, visualizing the important thing, how these spheres intersect these planes and which part of that lies within the unit cell. Okay. So, you can see here that these 60 degree totally do not even give a single atom, and therefore, my packing fraction of the 111 plane is the least here. Similarly, I can do my calculation for the FCC, again noting the fact that how atoms sit. So, this is my plane, the 100 plane in FCC, and you can see that it has the central atom plus 4 corners of atoms. The 110 plane has lot of space here, you can see in the middle, and therefore, it has a lower packing fraction, and the 111 plane is got the highest packing fraction, and it turns out to be, you can see it is closely packed along the plane. As you already seen, this is nothing, the 111 plane in FCC is nothing but the hexagonal layer, which is the close packed layer. So, it is not surprising for us that the 111 plane in FCC has the highest packing density. Similarly, we can do so in the BCC, and you can see that the 111 plane has the lowest density, which is also seen from this figure that most of the 111 plane is not occupied by atoms. And I had made a warning when we talked about Miller indices, that when I am taking a plane to do the calculation, I have to make sure that plane is a space filling plane. In other words, the part of the plane which lies in the unit cell, if repeated, should actually fill the entire 2-dimensional plane. Like I told you that suppose I take a 111 plane, and the two possibilities of picking the 111 plane, one plane which is a typical one, let me draw that again on the board for you. So, this is my 111, but I cannot pick a plane which is of hexagonal shape which lies between these two planes, because that plane we saw was not a space filling plane. Therefore, if you make use such a plane for calculation of this atomic density, you will land up with erroneous values. The next important topic we consider now is the topic of voids. Now, we already seen that the spheres, the atoms themselves do not fill the entire space, and this is reflected in the packing fraction being smaller than 1. This implies that there are voids between atoms, and lower the packing fraction, larger is the volume occupied by these voids. As we shall see, these voids have complicated shapes, but we are mostly interested in the larger sphere which can fit into these voids. Typically, we will assume that not only is the basic lattice or the basic crystal made of spheres, but we will also assume for now that actually the atom going into these interstitial, which is what we are interested in, are also spheres. Typically, we will consider only a plane faced polyhedron version of these voids and not actually the complicated shape of the voids, and what I mean by this I will show using models very soon. The size and distribution of the voids in materials play an important role in determining aspects, and many of these aspects of material behavior, for instance solubility of interstitial, the diffusivity, and many other important behavior wherein I need to consider these voids and the atoms which sit in these voids. That means I am not only interested in the packing fraction, but I am also interested in the shape of these voids and the size of these voids. Okay. And I am talking about shape, as I again emphasize, I am talking about the polyhedron version of the void and not on the real shape of the void. Now, the position of voids of a particular type will be consistent with the symmetry of the crystal. So, I will mention this by actually giving examples later when we consider the for instance the FCC and HCP crystals and also the BCC crystal. In close packed crystals, the FCC and HCP for instance, or what we call the CCP and HCP, there are two type of voids, the tetrahedral void and the octahedral void, and we will take up these two kind of voids in detail in these two structures. And the important point to note is that they are identical in both these two structures. That means as far as the void picture of these structures goes, I can have, and we already seen that when you are dealing with crystal structures, we have especially 4 important types of models we work with: the wireframe model, the ball and stick model, the space filling model, and the last but not the least, the void model. And these voids themselves can actually be put together to make an entire structure which is a space filling structure. So, when I want to make a space filling structure for these close packed structures, the FCC and HCP, I would use the octahedron, the regular octahedron and the regular tetrahedron, which I have seen before. For instance, now in these two structures, I have my regular octahedron and my regular tetrahedron, and these two will put together form the space filling unit, as we shall see. Now, one important point to note, whenever I mention the word octahedral, I should not be confused with the fact that the coordination number, even though when I am saying octahedron, actually the octahedron is 8 faces, but the coordination number is only 6. So, I should not confuse octahedral void meaning actually a coordination number of 8. Okay. So, this aspect has to be kept in mind. The other important thing we will see is that the BCC crystal, which we have seen already is not a close packed crystal, does not have a regular shaped void. That means it does not have a, it also has an octahedron and tetrahedron, but these two shapes, the octahedron and the tetrahedron, are not the regular octahedron and the regular tetrahedron. And we will see later that the octahedral void in fact can function like a linear void. So, what we mean by that also we will see. That means it does not have, could turn out that the coordination number is not 6, but actually 2. So, before we go take up the voids in the close packed structure, let me revise some of the points by actually taking an example. The first one I would like to mention is the example of the polyhedron version. So, let me take for instance a simple cubic crystal which I form here within this box with glass beads. So, you can see that there are 8 spheres, and now these are glass spheres which I put inside this unit cell to actually form a crystal. So, you can see here. Now, when I want to consider for instance the largest size sphere which I can put into this void, I have already done so by putting a golden shaped sphere. Is it clear from that? I hope it is clear from that camera angle to see that there is a sphere within the void. And let me show this by this pointer. I already put a sphere, and this is the largest sphere which would fit into this void without actually distorting this structure. So, when I am talking about this central atom, it is coordinated to these 8 atoms which are at the corners of the cube. If I were actually to consider the actual shape of this void, which is a little more complicated shape, I have a model right here, and I have done this by actually pouring wax into this model and taking out the spheres. So, you can see that actually the voids is considerable, the amount of volume occupied void is considerable, and it is in a very complicated shape. It has got curved faces, it has got straight faces. For the straight faces means basically that you are truncating it along the unit cell faces. So, but it is a complicated shaped polyhedron. But when I am talking about voids, I am not going to be considering this shape of the void, the true shape of the void, but what I might call the polyhedron version of this void. So, what I mean by the polyhedron version is a version which we saw before, a version like this. In other words, I will only talk about the vertices of the atoms around the void which form a polyhedron, and this polyhedron in this case happens to be the cube, which is around the central position where the what you might call an impurity atom or an alloying element atom can sit. So, in future I have to remember, even though these voids have very complicated shapes and complicated connectivity, and for instance this kind of voids would actually, this kind of space would actually connect in 3 dimensions along the 3 directions and form a continuous network, but I am not considering a shape like this, but I am only considering a shape like this when I am talking about voids. So, this aspect has to be absolutely clear. And what I am worried about when I am actually talking about these voids, the important question, first question I would like to ask is, what is the largest size sphere which I can put into this void without causing distortion to the celacity? And as we shall see, why I need to know this, suppose I am adding an alloying element which does not occupy the lattice position. Of course, I have 2 possibilities when I add an alloying element. The alloying element can go and replace this atom at the lattice position, like I could take an alloying element for instance wherein my sphere would be replaced by another. So, this is called a substitution alloying element, as we shall see later, but we could have an alloying element which does not go take up the substitutional position, but actually takes the interstitial position, which is what an atom has done in this case, which is the golden colored atom in the center. So, let us see these 3 structures or these 3 representations of the void a little more carefully in projection before we take up the next topic. So, I have here my true shape of a void, of course, the true shape which lies within a unit cell like this, the polyhedral version, in this case for the simple cubic happens to be a cube, and also the version wherein I have a sphere fitting inside the void. Though I am interested only in the sphere actually which needs to sit in the void most of the time, but I will have a representation in terms of the polyhedron, and rarely will I deal with the actual shape of the void in my representations. So, let me zoom in into this planar geometry to actually show you how this shape looks a little better. I am seeing the crystal along the 001 direction, wherein I have the 8 glass spheres which are now my atomic positions, and now the central sphere which is the largest size sphere which can fit into this void. As you can clearly see in simple cubic, the void size is very large, and also we have already seen the packing fraction is small. So, also we need, this is another important point we will see when you are talking about crystals, is not only the total amount of void which is available, but how they are split into these various void shapes and how we can actually put atoms into that. That will actually go on to determine my solubility, and therefore, it is not just the packing fraction which will determine my solubility. I need to know the shape of the voids and the largest sphere which can fit into those voids. In the cubic closed packed crystal, we have 2 kinds of voids, the octahedral void and the tetrahedral void, and we will consider these 2 voids in little detail. The tetrahedral void is located quarter way along the body diagonal, and I am saying that I mean the center of the tetrahedral void is located a quarter way along the body diagonal. And now, when I have a single tetrahedron located like this, then all the symmetry operations of the CCP crystal will operate on this tetrahedral void and give me the remaining tetrahedral voids, and as we shall see, there will be 8 such tetrahedral voids. Now, the volume occupied by the tetrahedral voids is 1/24 the volume of the unit cell. That is an important number, because now that will tell you that how big a sphere, this will give a measure of how big a sphere which can actually sit in this tetrahedral void. And when I am talking about symmetry operations which generate the remaining tetrahedral voids, I would also use my phase centering translations to generate the remaining voids. So, let us see where this tetrahedral void is located within the unit cell in an actual model. So you can see here a model like this, and ignoring these blue straws, I have to take this blue tetrahedron which is sitting inside the unit cell. So you can see the tetrahedron within the unit cell, and I have to remember that, for instance, every vertex of my cube is identical. Therefore, if I have a one tetrahedron sitting from pointed to this origin, then there will be one tetrahedron here, one here, one here, one here, and one here. So actually I will have 8 tetrahedron within a single unit cell, which is shown in this model here. So I have 8 tetrahedron, each one having starting from a vertex. So I have 8 tetrahedron sit within the unit cell. So you can clearly see this model. So I will have 8 tetrahedral voids within unit cell, and so the total volume of the unit cell which is occupied by tetrahedral voids will be 8 times 24, which is about 1/4. Now the octahedral void, and as I mentioned, the octahedral void implies a coordination number 6, is one of these octahedral voids is located at the center of the unit cell. That means if I place a small sphere in the center, it will actually be touching all the 6 atoms at the vertices of the octahedron, and therefore this is my octahedral void. So, but if there is octahedral half, then I can apply all my symmetries of the cube to obtain all the other octahedral voids in the CCP structure. The volume of the octahedral void is 1/6 the volume of the unit cell, which clearly tells me it is a much bigger void than the tetrahedral void. So the two voids I am talking about here, again to emphasize that these are the polyhedral versions of the voids I am talking. I have the tetrahedral void and the octahedral void. There are 8 of these tetrahedral voids, and we will soon see that we will make a calculation of number of octahedral voids per cell. Now, if, as I mentioned, I can apply all the symmetry elements to generate the remaining voids, and let me try to do that for the octahedral void. Now, and these includes the lattice translations. So let me repeat, once we know the position of a void, then we can use the symmetry operations of the crystal to locate the other voids. This includes lattice translations, and this is important because often by the way we draw some of these voids in the unit cell, they may look different, but we have to remember, since it is just the origin of the unit cell we have chosen differently, which makes them look different, but actually they are identical. So for instance, suppose I have a octahedral void at half, and I know my phase centering translation, which is a fundamental lattice translation vector of the FCC lattice, which is half, 0. I add to that, I get 1, half, which is nothing but 0, 0, half. Then clearly I know that if half is the seat of an center of an octahedral void, then 0, 0, half, which is nothing but the edge center, is also an equivalent site, and therefore will also be a site of the center of the another octahedral void. So this is, for instance, shown here in this picture. So I have these 4 cubic unit cells, FCC unit cells, and this center, which is located at a position like, for instance, 0, 0, half. Let me draw this, is actually a seat of the octahedral void, this position. So all edges, since no edge is different from any other edge, would be a seat of the octahedral void. So this edge, and so forth. So there are 12 edges to the cube, and all the edge centers are also positions of the octahedral void, and I can understand that purely by using the phase centering translation, knowing that the body center is a seat of the octahedral void. Now, if I look, the central octahedral void has a complete contribution to the unit cell. In other words, it is completely contained within the unit cell, as you saw here, and therefore an atom sitting in its center will contribute totally to this current unit cell when I am trying to make calculations of number of octahedral voids or number of atoms within the octahedral void per cell. But these octahedral voids sitting on the edges have only 1/4 content within the unit cell, and we will, of course, we have models to show you how we can visualize this 1/4 content. Therefore, their contribution to the unit cell will be 1/4. I have 12 edges with 1/4, so I have contribution of 3 from those in the edges, 1 from the center. Therefore, I have 4 octahedral voids per unit cell in an FCC structure, cubic closed pack structure. And as you know that there are 4 atoms in a unit cell in an FCC crystal structure, there are 4 octahedral voids. That means for every atom I have an octahedral void in a cubic closed pack structure. On the other hand, we have seen that purely based on symmetry arguments, if this is my center of a tetrahedral void, the quarter position, then I should have 8 of these tetrahedra within the unit cell, since I have only 4 atoms in this unit cell, that means per atom I have twice the number of tetrahedral voids. That means there are 8 tetrahedral voids per cell. This is something which is important to note. So let me tabulate these values before I show you some models to better visualize these octahedral and tetrahedral voids. The tetrahedral void is located 1/4 way from each vertex along the body diagonals. There are 8 voids per cell, and since there are 4 atoms per cell, there are twice 2 voids per atom. So there are 2 tetrahedral voids per atom. The octahedral void is located at half half half, which is nothing but the body centering position. It is also located at the edge center, which is half 0 0 and equivalent positions. So there are 4 voids per cell, and as we saw that the ones at the edges only contribute 1/4 to the unit cell, and the number of voids per atom is 1 octahedral void per atom. So let me try to visualize these things using models before I take up the calculations based on the largest sphere which can fit into these models. So I got models here, and I will show them from both the angular perspective and also from the other perspective. So let me show this model. For instance, I got a model here with sphere. This is what I call the space filling model, and you can see these 4 red colored balls actually try to locate my tetrahedral void. That means the center of these 4 tetrahedral atoms is my seat of the tetrahedral void. So this is just, we have to remember that all the spheres represent the same kind of atoms, and these 4 have been colored differently just to locate my position of the tetrahedral void. And if I have 1 here, then obviously each one of these vertex will also be a starting point of the tetrahedral void. So I will have 8 of them, as is seen from this other model, wireframe model. So I have 1 tetrahedral void center here. So let me use a stick to point as a pointer. So there will be 1 here, 1 here, which will be related by a 4-fold along this direction. There will be 1 here again by 4-fold rotation, and there will be 1 here. Similarly, there will be 1 here, 1 here, 1 here, and 1 here. Since the cubic closed pack crystal has 4-fold rotation, they are all equivalent positions, and I have 8 of these tetrahedral voids. Now let me take the same model to actually generate the structure wherein I have an octahedral void. So let me try to take these spheres and make an octahedral void. So I hope some of this is visible from the camera angle from there. So you can see this, are able to see this? Okay. So I am trying to make an octahedral void in this structure. So this is my octahedron which is sitting within the unit cell. So this is my space filling model wherein I have used different colors of ball to send for the atom sitting in the face centering position to show you the position or the shape of the octahedral. That means an atom sitting at the center of the octahedral void, and if of the right size will actually be touching the atoms in the red color or the orange color. These colored balls will be touching, and you can clearly see it is a 6 coordination. Now as I mentioned, one of the important questions we are trying to ask ourselves when we are dealing with voids is with respect to alloying elements, is with respect to the largest sphere which can fit into these voids. So in this calculation, let me try to find the largest sphere which can fit into the tetrahedral void and the largest sphere which can fit into the octahedral void in the cubic closed pack crystal. Now let me consider the tetrahedron as shown here, and the distance CV is nothing but the radius of the parent atom which is occupying the lattice positions, and the radius of the new atom which is going to sit in the center. So this is my atom going to sit in the tetrahedral center. So this center of this point here to the vertex is r plus x, where x is the radius of the foreign atom. Now this distance CV is equal to root 6 by 4e from geometry, and therefore I get that is equal to r plus x. Now I know E is equal to 2r because atoms are touching along the tetrahedral voids, and that is, this implies x by r is root 3 by 2 minus 1, which is equal to 0.225. So x by r is the ratio of the largest sphere which sits in the interstitial tetrahedral position to the largest or to the sphere which is sitting in the lattice position. So, ratio of these two radii is 0.225. So, it is approximately this number, and that means if I put a sphere larger than this size, then it is going to push my atoms around the lattice position and cause distortion. If I put an atom smaller than this size, then it will tend to rattle around within that void, assuming that it is a hard sphere model. So, both these situations are not favorable. In other words, if I have a smaller size sphere, then it will not be bonded properly to the 4 atoms around this tetrahedral void position, these 4 atoms, and if I put a larger size atom, it is going to cause strain in the lattice. Therefore, the correct size sphere which can fit into this void is a sphere whose radius which is about 22.5% of that the radius of the atom at the lattice positions. Now, the size of the largest atom which can fit into the octahedral void in this cubic close packed crystal, again I can make a calculation that the center to the vertex distance. So, this is my center of the void, to my vertex distance is 2r plus 2x, and which is equal to a, and we already know for the FCC crystal it is root 2a is equal to 4r. So, I can calculate my x by r as root 2 minus 1, which is 0.414 approximately. In other words, the octahedral void in the cubic close packed crystal is almost double the size of the tetrahedral void. The tetrahedral void is very small, and the octahedral void is a much larger void in the cubic close packed crystal. And this is an important point to note, and later on we will try to compare these sizes like the 22.225 and 0.414 with some of the other void sizes in the BCC crystal. Now, in the case of the hexagonal close packed crystal,